In today's video, we will be going over separable equations and their applications to certain scenarios involving differential equations. For our first set of problems, we have been asked to find a function that is a solution of the given differential equation. In our first problem, they have given us dy dx is equal to x squared divided by y times the quantity 1 plus x to the third power. We can begin by moving all the terms with y in them to the left side of the equation and all the terms with x to the right side of the equation. By multiplying by y, we get y times dy, and by multiplying by dx, we get x squared over 1 plus x to the third power times dx. We can then take the integral of both sides of this equation. Taking the integral of y times dy will give us 1/2 times y squared. And the integral of the right side of the equation will require a u substitution where u is equal to 1 plus x to the third power, and so du will be equal to x squared times 3. As a result of this u substitution, the right side of our equation after taking the integral will become 1/3 times the natural log of 1 plus x to the third power plus some constant c. Simplifying this equation and making it such that the entire thing is equal to y, we'll find that y is going to be equal to the square root of 2/3 times the natural log of 1 plus x to the third power plus c. For our next problem, we are told that x times dy dx needs to be equal to 1 minus y squared, the entire quantity to the 0.5 power. Moving all of the terms with x in them to the right side of the equation and all of the terms with y in them to the left side of the equation, we can rewrite this entire thing as 1 over x dx is equal to 1 over the square root of 1 minus y squared dy. Taking the integral of both sides of this equation, the integral of 1 over x will be equal to the natural log of x plus some constant c, and that will be equal to the integral of the right side of our equation. The right side of our equation may look familiar. It means that the integral of the right side is equal to the inverse sine of y. And so simplifying this entire equation to make it equal to y, we find that y is going to be equal to the sine of the quantity natural log of x plus c. For our next problem, we are told that carbon taken from an ancient piece of building material contained only 33% as much carbon-14 as carbon taken from present-day building materials, and they want us to identify how old the piece of material is. In order to solve this problem, we need to use the equation dn over dt is equal to negative k times n, where n is the number of atoms of carbon-14 in the substance, and k is a constant which depends on the particular radioactive isotope. Moving all of the terms with t to the right side of this equation and all of the terms with n to the left side of this equation, we can find that 1 over n times dn will be equal to negative k times dt. We can then take the integral of both the left and right side of this equation, and so we get the natural log of n is going to be equal to negative k times t plus c. By taking this entire equation as e to the power of both sides, we then get n is equal to e to the negative kt plus c power. Replacing e to the c power with some constant a, we can then rewrite this as n is going to be equal to a times e to the negative kt power. By plugging in t equal to 0, e to the 0 power will be equal to 1, and so we find that n sub 0, or the initial amount of carbon-14 in the substance, will be equal to a. And so we can rewrite this equation as n is equal to n sub 0 times e to the negative kt power. We can then divide both sides by n sub 0, and so we get n over n sub 0 is equal to e to the negative kt power. Given that we know that the old material has 33% of a typical piece of carbon-14, we can then rewrite this as 0.33 must be equal to e to the negative kt power. As was previously stated, the constant K is dependent on the particular radioactive isotope. For carbon-14, the constant K is known to be equal to 0.0001216. And so plugging K into the equation, we have 0.33 must be equal to e to the negative 0.0001216 times t power. Solving this equation for t, we find that it is equal to 9,117, and it will be in the unit of years. And this is because the constant k is dependent on t being measured in years. For our next problem, we are told that we recently found a credit card bill in a pile of mail in the house from 4 years ago that required the payment of $70. If the late payment fine grows exponentially at a 15% monthly rate, how much do you now owe the credit card company? In order to solve this problem, we must use the compound interest equation. dA over dt is equal to R times A. In this equation, R is our interest rate and A is the amount of money. We must keep in mind that because we are given the monthly rate, our time must also be in months. And so 4 years is equivalent to 48 months. Solving for this differential equation, we move all the terms with t to the right-hand side and all of the terms with a to the left-hand side, and so we get 1 over a times dA will be equal to r times dt. Taking the integral of both sides of this equation, we find that the natural log of a is going to be equal to r times t plus some constant c. Putting e to the power of both sides of this equation, we find that a is equal to e to the r times t plus c power. Replacing e to the power of c with some constant a sub 0, we can then rewrite this equation as a is equal to a sub 0 times e to the rt power. In this case, a sub 0 will be the initial amount of money that we owe to the credit card company. And so, solving this equation, a is equal to the initial amount of money we owe, $70, times e to the monthly rate of 0.15 multiplied by the amount of time in months, so 48 months. And so it can be found that the amount of money that we now owe the credit card company is $93,760. For our last problem, we are told that a glass of water is set outside on the porch of a Michigan resident in the middle of the winter. If the temperature of the water was initially at 45 degrees Celsius, and after 15 minutes the outside temperature of 5 degrees Celsius has cooled the water to 17 degrees Celsius, at what time will the water be at 10 degrees Celsius? Solving for this problem requires the use of Newton's law of cooling, which is dT, large T being the temperature, over d small t for the time, must be equal to K multiplied by A minus T. And in this equation, A is the temperature of the medium, or in this case the outside air, and T is the temperature of the substance, or in this case the water. Moving all of the terms with large T for temperature to one side of the equation and all of the terms with T to the other side of the equation for time, we have 1 over A minus T, and A is equal to 5 degrees Celsius, and so we have 5 minus capital T times D capital T is equal to K times D little t for time. Taking the integral of both sides of this expression, we find that the left side is going to be equal to the negative natural log of 5 minus capital T, and that is equal to the integral of the right-hand side, K times T plus some constant C. Taking e to the power of both sides of this expression, we can rewrite this equation as 5 minus T must be equal to e to the negative kt plus c power, The negative here is a result of the negative that was previously in front of the natural log side of our equation. And so by replacing e to the c power with some constant b, we can rewrite this equation as 5 minus t is equal to b times e to the negative k times t power. We can solve for b at the initial point of this problem where the temperature of the water is equal to 45 degrees Celsius, and that will be equal to b times e to the negative k times 0 for time power, and so b must be equal to negative 40. We can now rewrite the equation as 5 minus t is equal to negative 40 e to the negative k times t power. And so t is going to be equal to 40 times e to the negative k t power plus 5. Solving for the constant k requires that we plug in the known temperature of 17 degrees Celsius at the known time of 15 minutes. So we have 40 times e to the negative k times 15 plus 5. Solving for k in this equation, we find that it is equal to 0.08026. We can then solve for the time at which the water will be at 10 degrees Celsius. And so we have 10 must be equal to 40 times e to the negative 0.08026 times t power plus 5. And solving for t, we find that the water will achieve a temperature of 10 degrees Celsius at a time of 25.9 minutes. That concludes this video on separable equations and their applications to certain scenarios.